The Moon is Earth's only natural satellite, and by far the most thoroughly studied body in the solar system beyond the Earth itself, the one other world from which we have carried home rock in our own hands. It is also in one important sense an oddity. Though only about a quarter the diameter of the Earth and an 81st of its mass, the Moon is enormous in proportion to the planet it circles. No other major planet has a satellite so large a fraction of itself, and this striking mismatch is the first fact any account of the Moon's origin must explain. It orbits at an average distance of some 384,000 kilometers, taking a little over 27 days to circle the Earth against the stars, and it turns on its axis in exactly that same time, so that one hemisphere, the near side, faces us perpetually while the far side is forever turned away. That far side is not a dark side. Over a month it receives just as much sunlight as the face we see. It is simply hidden, the natural result of the tides having long ago locked the Moon's spin to its orbit. That perpetual turning of one face is not the Moon's only clue to its nature. Its weight is another. For its size, the Moon is curiously light. Its average density is only about 3 1/3 times that of water, barely 60% of the Earth's. A rocky world this undense cannot hold much iron, and indeed the Moon has only a very small metallic core, quite unlike the great iron heart that makes the Earth so dense. This single fact, a Moon deficient in iron, and disproportionately large besides, is the central constraint on every theory of how it came to be. A world captured from elsewhere, or spun off from the Earth, or built alongside it from the same material, ought not to look so different in composition from its host. The Moon's lightness, its missing iron, and its very size together point insistently toward a more violent and particular kind of beginning. That beginning in the leading account was a catastrophe. Roughly 4.5 billion years ago, when the Earth was still young and not yet finished forming, a wandering body about the size of Mars, given the name Theia, struck the proto-Earth a colossal, glancing blow. The energy of the collision flung a vast quantity of vaporized and molten rock into orbit, torn mostly from the rocky outer layers of the two worlds, and from that hot, whirling disk of debris, the Moon swiftly gathered itself together. The metallic cores of both bodies, meanwhile, merged and sank into the Earth. This single event accounts at a stroke for the puzzles we have met. The Moon is iron-poor because it formed from silicate debris after the iron had drained away into the Earth. It is depleted in the easily boiled volatile elements because it condensed from ferociously hot ejector, and the impact itself supplied the great spin of the Earth-Moon system. It is a theory born of violence, and it has held the field for half a century. Yet the giant impact carries a deep and stubborn difficulty. Every body in the solar system bears a distinct chemical fingerprint in the proportions of its oxygen isotopes, a signature as individual as a barcode, differing from world to world. If the Moon were built largely from Theia as the simplest simulations predict, it should carry Theia's fingerprint, plainly different from the Earth's. Instead, the rocks of the Moon and the rocks of the Earth's mantle are isotopically almost identical, matching to within a few parts in a million. This is the isotopic crisis, and it has forced the theory to grow subtler. Perhaps the impact was so violent that the Earth and the debris merged into a single connected cloud of vapor, a structure sometimes called a synestia, churning and mixing so thoroughly that any difference between the two was erased before the Moon condensed within it. Perhaps Theia, forming at the same distance from the Sun, simply shared the Earth's composition to begin with. The giant impact itself is not in doubt, but its exact geometry and the mixing that made Moon and Earth so alike remain genuinely open questions. It is worth seeing why this violent idea triumphed over the gentler ones it replaced. 3 older theories, each founded on a single physical objection, capture the notion that the Moon formed elsewhere and was later seized by the Earth's gravity, founders because a passing body does not simply halt and settle into orbit. Without some third agent to absorb its enormous excess energy, it swings past and away again. Fission, the idea that a fast-spinning young Earth flung off a blob that became the Moon, demands an impossibly rapid initial spin and cannot account for the system's angular momentum. And co-accretion, the Moon and Earth condensing side by side from the same swarm, cannot explain why the two ended up so different in density and iron. The giant impact answers all 3 objections together. It supplies the angular momentum from the collision, it drains the iron into the Earth while launching iron-poor rock into orbit, and it processes that rock at high temperature to strip its volatiles. Where each of the others failed at a single point, it succeeds at all of them at once. How old is the Moon? The radioactive clocks locked into its rocks place its formation between about 4 1/3 and 4.5 billion years ago, and the very spread of the answers is itself informative. One family of measurements tracking the decay of a form of hafnium into tungsten and the ages of tiny zircon crystals points to the Moon's crust having formed as early as 4.5 billion years ago, within the first 60 million years of the solar system. Another cluster of ages falls a little later, near 4.1/3 billion years, and the most recent interpretation reads this not as the Moon's birth, but as the scar of a later event, a great remelting, as the young Moon's orbit evolved and tides heated its interior, which reset many of the rock's clocks. In this view, the Moon is genuinely ancient, formed close to 4.5 billion years ago, but much of its recorded history was overprinted, its stony memory partly rewritten, 100 million years or so after it was born. The Moon has become, in fact, the master clock of the whole inner solar system, and it earns that role through its craters. Because it has no plate tectonics, no liquid water, and almost no atmosphere, its surfaces are not erased but preserved, holding the scars of impacts for billions of years. The principle is simple. The longer a surface has lain exposed, the more craters accumulate upon it, so that a heavily cratered terrain is old and a lightly cratered one young. The crucial step was calibration, by counting the craters at the exact spots where Apollo and the Soviet lunar missions collected rock, and then dating those rocks in the laboratory. Scientists tied crater density to absolute age, and that lunar calibration is now stretched across the solar system to date the surfaces of Mercury, Mars, and the moons of the giant planets where no one has ever gathered a sample. It is why China's recent returns of rock from terrains the Apollo astronauts never visited are so prized. They test and extend the master clock in the ages where it was least secure. The giant impact left the newborn Moon glowing hot enough that a great fraction of its outer body, perhaps its entire rocky mantle, was molten, a global ocean of magma hundreds of kilometers deep. The slow cooling and freezing of that magma-ocean is the single most important event in the Moon's chemical history, for it sorted the young world into the layers we see today. As the melt crystallized, its minerals separated by weight. The dense, iron and magnesium-rich crystals that formed first sank downward, building the deep mantle. But one common mineral, the feldspar called plagioclase, is lighter than the melt from which it grows, and so it floated, rising to the top and gathering over time into a buoyant crust of pale rock. That floated scum of feldspar is the bright lunar highlands we see with the naked eye. The Moon's original crust is, quite literally, a layer of frozen froth skimmed from a planetary sea of fire. The last dregs of that great freezing tell their own story. As the magma-ocean crystallized, a handful of elements that fit awkwardly into the common minerals, potassium, the rare earth elements, phosphorus, and the radioactive heat producers, were progressively left behind in the shrinking pool of residual liquid, until they were concentrated into a distinctive final layer trapped beneath the crust, a component geochemists know by an acronym drawn from its ingredients, and one that would later shape the Moon's volcanism. The whole model is beautifully confirmed by a chemical fingerprint the rocks carry. An anomaly in the element europium, which under the Moon's conditions slips easily into floating plagioclase, and is therefore enriched in the highland crust and correspondingly missing from the rocks that formed elsewhere. The presence or absence of that europium signature in a lunar sample is a direct readout of its relationship to the ancient flotation crust, a piece of the magma-ocean's logic, written into every stone. What of the Moon's inside? It has been reconstructed from 3 sources: the seismometers the Apollo astronauts left behind, which listened for years to the faint trembling of moonquakes, the exquisitely precise mapping of the Moon's gravity by a pair of orbiting spacecraft, and the laser ranging that measures how the Moon flexes and wobbles. Together they reveal a layered world. The crust proved thinner than once believed, on average only some 35 to 40 kilometers, and riddled with the porosity of eons of shattering impacts, and markedly lopsided, thinner beneath the near side than the far. Below it lies a thick rocky mantle, and at the center a small iron core, perhaps 350 kilometers across, only a fifth of the Moon's radius, a fraction far smaller than the Earth's, exactly as the giant impact predicts. And that core is not entirely frozen. Its outer part appears still to be molten, which means the early Moon, like the Earth, may once have generated a magnetic field of its own, though it has none today. Turn a pair of binoculars on the Moon, and its 2 great terrains leap into view. The bright, rugged, heavily cratered highlands, And the dark, smooth, rounded plains the early astronomers mistook for seas and named them Marea, Latin for seas, though not a drop of water was ever in them. The two could hardly be more different in age or origin. The pale highlands are the moon's ancient original crust, that floated feldspar, saturated with craters because they have lain exposed to bombardment since almost the beginning, and they cover most of the surface and nearly all of the hidden far side. The dark Marea, by contrast, are far younger, and they are concentrated overwhelmingly on the near side that faces the Earth. This lopsidedness, pale rough highlands wrapped around most of the globe, dark smooth plains pooled on the side toward us, is among the moon's most striking and long puzzling features, and the plains hold the key to it, for the Marea are frozen floods of lava. Long after the magma-ocean had solidified, the deep mantle reheated, partly melted once more, and dark, iron-rich basalt welled up to flood the floors of the great impact basins that earlier collisions had gouged into the near side. This volcanism ran for an astonishingly long time, the main outpourings from about 4 billion years ago to little more than 1 billion, and in places later still. Its concentration on the near side is tied to a single region unusually rich in those leftover radioactive heat-producing elements, whose warmth kept the underlying mantle melting for far longer than elsewhere on the moon, and the Chinese sample return missions of recent years have stretched the story further than the Apollo rocks ever hinted. Near-side basalts only 2 billion years old, and, from the first samples ever brought back from the far side, lavas that erupted there some 2 4/5 billion years ago. The moon, it turns out, stayed warm and volcanically alive far longer than we once believed. The moon has no atmosphere worth the name, only a ghost of an exosphere so thin its atoms scarcely meet, and so its surface lies utterly exposed to everything space can throw at it: the ceaseless rain of micrometeorites, the streaming solar wind, the cosmic rays, and the brutal swing of temperature. Over billions of years, this bombardment has ground the outermost rock into a blanket of powdery, shattered debris called the regolith, several meters deep over the younger plains and thicker still over the ancient highlands. The endless micro-impacts weld grains of soil into little glass-bonded clumps, implant hydrogen and helium from the solar wind into the surface of every grain, and coat the soil in a film of vanishingly small iron particles that slowly darken it and redden the way it reflects light. This gradual maturing under exposure, space weathering, is why the freshest soil, splashed out by a recent crater, looks brighter and bluer than the old, dark, weathered ground around it. The surface is also a place of ferocious temperature. With no air to soften the sun's glare or hold in the warmth, and a day and a night each lasting some 14 Earth days, the equatorial ground swings from around 120 degrees above freezing at noon to 170 below at night. The most extreme readings of all come from the poles. There, on the floors of certain deep craters that the low-riding polar sun can never reach, an orbiting spacecraft has measured temperatures near 20 Kelvin, around -250 Celsius, among the very coldest places known anywhere in the solar system. The powdery soil is a superb insulator, so that just a little way below the surface the wild swings give way to a steady, moderate chill. But on the surface itself, and above all in those eternally shadowed polar pits, the moon holds cold as deep as almost anywhere in the sun's whole domain. And that bitter polar cold, it turns out, is precious. For most of the space age, the moon was thought to be utterly bone dry, its every drop of water long since boiled away. That belief has been overturned, and lunar water is now among the strongest reasons to go back. The evidence came in stages. In the 1990s, an orbiter sensed a concentration of hydrogen at both poles, hinting at buried ice. In 2009, a spacecraft was deliberately crashed into a shadowed polar crater, and instruments watching the plume of debris it kicked up found the clear spectral signatures of water, several % of the excavated soil by weight. And in 2020, an airborne infrared observatory detected water molecules even in sunlit soil far from the poles, bound up somehow in the grains and glasses. This, lunar water, is a mixture of true water, of the closely related hydroxyl, and of implanted hydrogen, delivered over the ages by comets and asteroids, forged from the solar wind striking the soil, and in part retained from the moon's own fiery interior. The polar ice survives because of a quirk of the moon's posture. Its axis stands very nearly upright, tilted barely 1.5 degrees, so that near the poles the sun forever skims the horizon and never climbs high enough to shine into the deepest crater floors. Those floors have lain in unbroken darkness not for a night or a season but for billions of years, and they are so cold that ice, once it arrives, essentially cannot leave. The rate at which it evaporates into the vacuum is so slow that a layer would take longer than the whole age of the solar system to disappear. Each such crater is a one-way trap, patiently gathering and holding every volatile that wanders in. This makes the ice doubly precious. It is a potential resource, water that could be split into breathable oxygen and rocket fuel, and it is a scientific treasure, a frozen archive of every comet and every whisper of solar wind that has touched this corner of space, a record of where the inner solar system's water came from that has no equal on our own restless, weathered Earth. The moon was transformed from a light in the sky into a sampled world by the great exploration of the 1960s and 70s. Between 1969 and 1972, 6 American Apollo missions set 12 men on the surface and brought home some 380 kilograms of rock and soil, thousands of carefully catalogued samples that remain, half a century on, the bedrock of lunar science. It was these rocks that yielded the ages behind the cratering clock, the floated pale anorthosite that proved the magma-ocean, and the instruments that probed the interior. The Soviet Union, in parallel, sent its robotic lunar craft to make the first soft landing and to scoop and return smaller samples by machine from places the Americans never went. And, among the gear the astronauts left behind, were simple arrays of mirrors that need no power targets for laser beams fired from Earth, still in use today, measuring the distance to the moon to within a centimeter more than 50 years later. Those laser mirrors reveal something quietly profound. The moon is drifting away from us, receding at about 4 centimeters a year. It is the slow working of the tides. The moon raises a bulge in the Earth's oceans, and because the Earth spins faster than the moon orbits, that bulge is dragged ahead of the line between the two bodies, and its gravity tugs the moon forward, feeding energy into the moon's orbit and pushing it outward, while acting as a brake on the Earth's spin, so that our day is slowly lengthening by a couple of thousandths of a second each century. Run the process backward across the ages, and it tells us that the moon was once far closer to a young Earth that turned far faster, exactly the intimate, close in beginning that the giant impact demands. The moon's stately retreat and the Earth's slowing day are two faces of a single, ancient exchange of momentum between the two worlds. After a long pause, the moon returned to the heart of exploration, first through a fleet of orbiters that produced much of what this chapter describes. They mapped its composition, found the polar hydrogen, imaged the surface in fine detail, took the temperatures of the polar cold traps, and weighed the crust from orbit. Spacecraft from Europe, Japan, India, and China joined the American ones. Then the returning of rock resumed. China's Chang'e missions brought back near-side basalts far younger than any Apollo sample, and then achieved something never done before, the first return of rock from the moon's hidden far side. And landers began, for the first time, to reach the coveted South Pole. An Indian craft touched down there in 2023, and, soon after, the first commercial spacecraft ever to land on the moon arrived near the same region, a sign of how the character of lunar exploration is changing, from a contest of two superpowers into a broader and more crowded endeavor. And now the astronauts are preparing to return. Under the banner of the Artemis program, a first uncrewed flight sent a capsule around the moon and safely home again. A second, carrying 4 astronauts on a great loop around the far side, has followed, the first people to travel to the moon in more than half a century. The plan that lies ahead is to land a crew near the lunar South Pole and to build a small station in orbit about the moon as a waypoint. And the strategic logic behind all of it comes back to that polar ice. Water that can be mined and split into oxygen to breathe and hydrogen to burn would turn the moon from a mere destination into a kind of filling station, a stepping stone from which the exploration of the deeper solar system might one day be launched far more cheaply than from the bottom of the Earth's own gravity well. For all that it is a resource and a destination, the moon's deepest value is as a witness. Airless, waterless, and tectonically dead, it has forgotten nothing. Its cratered face preserves a record of the solar system's violent youth that our own restless, weathered planet erased long ago, and from that record we read the ages of worlds we can never sample. Its rocks, so like the Earth's, carry the memory of the catastrophe that made them both, and the ice hoarded in its dark polar traps holds a frozen history of where water, and perhaps the very ingredients of life, first came to the inner solar system. The moon is, in the end, a companion that doubles as an archive, the nearest of all worlds, the only one we have ever walked upon, and a key by which we read not just its own past, but the history of the Earth and of the whole family of planets to which we belong. To return to it is, in a real sense, to go back to the beginning of our own story.